First, happy birthday to Astronomy on Top. Yeah. And I would like to talk about understanding distant world, or actually what we are working on is what we know about planets in general and exoplanets in particular. So I would like to start with what is a planet? Planet is an intermediate mass object between these small objects like the moon and stars. So it shouldn't be massive, too massive, because then it becomes a star, but it also cannot be too small. Planet should orbit a star. This means that the moon is not a planet, and also other moons. Oh. And okay, another criterion which was added in 2006 is that planet should clean its orbit, and because of that, Pluto, which we also like, is not a planet anymore. It's called now a dwarf planet, and there are many other dwarf planets that are known in our system. So in order to understand planet, we should start with our solar system, because these were the first planet that we studied. And if we take a look in our solar system, here is the system. We have the sun in the middle. The closest to the sun are the terrestrial planets. These planets made of mainly rocks and iron, and they are pretty small in the order of the Earth's mass, and they're pretty close to the star. If we go further from the sun, we have the gas giants, which are Jupiter and Saturn. These planets are much more massive. Jupiter is more than 300 times the mass of Earth, and they made mainly of gases, mainly hydrogen and helium. If we go even further, we meet the ice giants, Uranus and Neptune, in our system, which are kind of intermediate mass planets, about 15 Earth masses, and they are made of a mix of rocks and also ices, because it's really cold there, and some gases as well. So just from observing our solar system, we can already see that if we are close to the sun, we have more rocks in the planets. If we get farther, we have more gases and ices, and the planets become more massive. And another thing that we can see, if we just take a look on this system, is that all the planets are in the same plane. And this can give us a clue about how planet formed, because it is not a coincidence that it's like that. So actually, planets form in a gas disk around a young star. This is the star in the middle. We start with a clump of gases, and as the star forms and all the system rotates, this becomes a disk. And we know that this disk exists. First it was theoretically, then we observed them. If we take a look, these are the protoplanetary disc, what we call the protoplanetary disc. These are disks of dust and gas and some rocks around young stars. So these two pictures are not real. They are artist drawing. But in the last few years, we have actually great pictures of real disks. These two disks are real. These are real photos of disks, and now we have tens of them, and the number continues to grow. So we really observe these disks, we really see them, and we know that these disks have some limited lifetime. So the disk is there, the planet form in it, and in some point the disk dissipates and we stay with the solar system. But the question is, what happened in between? How we switch from the disk phase to a distinct planets in orbiting this star. So there were, actually there still is, they still are, two main groups of planet formation mechanisms. One is the top-to-bottom mechanism, when within this disk there is some area that become unstable, dynamically unstable, and just collapse under its own gravity. And this means that it contracts. And during this contraction, the density there become high enough to form a gas giant planet. And this gas giant just go around in this disk, and when the disk dissipates, we stay with such a planet. The second mechanism is the bottom to top. In this protoplanetary disk, does it, because I'm moving? Yeah, I don't know where this noise come from, sorry. So in this disk we have some rocks which we call planetesimals, actually different size of rocks, starting from centimeter size to all the way to kilometers, and they just collide because all of this thing goes around the star. They collide. Some of these collisions lead to sticking of these parts, and in some point they become gravitationally bound. And this gravity, as this object grows, attracts more and more of these small stones to form a core of a planet. Now the question is, what happened first? Is the disk dissipate before we reach some critical mass, or do we have still enough time to accrete gas on top of it? So what we find in calculations is that when we have less than 5 Earth masses of this rocky object, it just remains rocks with a very tiny amount of gases on top of it. But if we cross the 10 Earth mass for this kind of core, we start to accrete gas very rapidly, and this gas leads to more gas being accreted because the mass increases very rapidly, and we end up with a giant planet. So currently, this theory more popular and more acceptable because it can explain both small planets like Earth and big planets like the gas giants. So actually, most of these theories were developed until the late 80s, and there was kind of feeling that, okay, we know everything already, we know how planets form, we know what's going on. And this was supposed to be the end of the story, although there were, of course, some missing pieces, but in general, this was the end of the story. But then, the exoplanet came. And it just changed the entire picture. All the games start from beginning because we study very different things than what we know in our solar system. So the first planet to be observed was in 95. This was a giant planet, very close to the star, and it was found by radial velocity. Later on, different methods to detect planets were developed, and several space missions and also ground-based telescopes were dedicated to look for planets, and these days we have thousands of known detected planets in our galaxy. Kamen is going to talk more about how we observe them and what are the methods, how it goes. Yeah, so currently we know a lot, as I said, thousands of planets. Some of them are even entire solar systems, or maybe not entire, but solar system by their own. And this shows us, here we see each of these nice circles is one solar system that was detected by the Kepler space mission. And we can learn from that, first, that our solar system is very not special. We have very, very different types of solar systems. But then we also want to take a look on the planets themselves and see what we can learn about them. So this is one of the important tools that helps us, the theoreticians, to study the planets. So here we see the planet mass on its axis. This is the planet mass. And here we have the distance from the star. And each dot is a planet. I removed the error bars so you can see something. Of course, there are some error bars on these measurements, not even negligible in some cases. And I put here the pictures of our solar system planet just for comparison. And as you can see, we get very different types of planets. Types that we can think about or imagine before we get known to the exoplanets. Like, for example, we have this type of planet here. These planets are very massive. As you see, more massive. As we go up means more massive. As we go to the right means more distance from the star. And you see that we have planets which are much more massive than Jupiter and very, very far out, like in the edges of the solar system. And these planets, most of them are young. I don't have enough time to explain you why, but they are young. And it's a question how we can form such a giant planet so far, like in the edge of the protoplanetary disk, so early in the evolution of this system. Another interesting group of planets is the hot Jupiters. We talk about Jupiter mass planets. Here they are. Jupiter mass planets, but extremely close to the star. Extremely close means much closer. Here is our Mercury. You see the distance? Much closer than that. They are in a several days orbit around the stars. Means that they finish an orbit in 1, 2, 3 days, although they are giant. How they get there? Is it possible to form it there? So these questions are still questions that people are working on. Another very nice group of planets, and as you can see, it's a very large group of planets, is the super-Earths and sub-Neptunes. We don't have an equivalent in our solar system for this kind of planets, but these planets are in intermediate mass, bigger than Earth, but smaller than Uranus and Neptune, and very close to their star. So if we take a look on this plot, we already can see that we have a lot of types of planets that it's very difficult to explain with the previous theories. Now, all this area here below is clean. Do you have any idea why it's clean? Yes? Exactly. It's too hard to observe this planet because we are talking about less massive planets, but further out from the, very distant from the star. Means that it's very difficult for us to detect them. But as there is some progress in observing method, we're going from here. These were the first planet to be observed. We go to this direction as the observation methods get improved. And hopefully, as you see, we are on the edge of looking for habitable planet, what we call, means planets that are potentially can have life on them. Because these planets in this region, which Earth is also part of it, are at the same mass as Earth, or similar mass, and similar distance from the star. Not too cold, not too hot, means that we may have life there. So as you see, we are really close to observe this, this region. So what we learned from these things, one of the studies is study the mass-radius relation of exoplanet. This is part of my work. What we actually do, for some planets, we have both measurements of radius and mass. From radius and mass, here is the radius of observed planet, here is the mass, and each dot, this time with the error bars, is a planet. From this radius mass, if we know both the radius and the mass of a sphere, we can say something about its mean density. And this mean density gives us a clue about what is the composition of this object. Like, these curves are theoretical calculation that we usually do for if the planet was composed of one material. So if it was only iron, it should fall like these planets are probably only iron, contain only iron. And these planets contain rock. This is Earth here, and Venus. So we can say that these planets, for example, must have some fraction of gases, probably hydrogen and helium, because otherwise they cannot have such a large radius for their for their mass. So these studies can help us understand what's going on inside, what is the interior composed of, and what are the processes that are going on in the interior of these planets. Another thing that we study is the habitability, how potentially they can have life on them. And here we see what we consider as the habitable zone. This is the blue part. This is the distance from the star. And this is the type of the star. If the star is a sun-like star, this is the distance that, of course, Earth is part of it, that should allow for life in terms of the temperature on top of it. If we go to more luminous stars, we should get further in order to reach this habitability zone. And if we have red dwarfs, for example, which are less luminous stars, we can be closer. And the TRAPPIST, I don't know if you heard about the TRAPPIST-1 system that were observed. These planets are much closer to the star, but yet can be habitable just because this star is much less luminous than our Earth. So since I don't have a lot of time in this talk, I will just mention some open questions that our groups worldwide working on in the topics of theoretical calculation of exoplanets. So first we want to explain how it's possible to have a Jupiter-like planet so close to its parent star, how it gets there and how it formed and what happened to it. Is it stable or does it just evaporate because of the radiation from the star? Second, there are some calculations of the disk itself and the gravitational perturbation within the disk in order to explain these further out giant planets. And is it possible to form them, and under which conditions, like what are the requirements of the disk in order to form this kind of planet? We also study migration. Migration is the idea of that may explain this kind of planets. That planet was formed further out, but then due some torques and forces migrated inward to a closer orbit. And this actually will help us answer the question, if we find a planet in a specific location, does it mean that it formed there? Or maybe it formed somewhere else and gets there during the lifetime of the disk. We also study how the interior of this planet was formed. Like, do we expect to have a solid core and on top of it a gaseous envelope? Or do we expect some of this material to dissolve in the envelope of the planet, and then we don't get this layer structure, but we get something more gradual. And these have a lot of implications about the heat transport in these objects. And finally, there are many, many topics of life-related subjects. Habitability, is the ocean is stable on top of a planet, yes or no? What is the biomarkers in the atmosphere, namely what are the atmospheric properties that we want to observe or we want to look for in other planets in order to check if it's possible to have life there or not. And I think that I stop here.